Kelly, we're going to look at all of these things that I have here on the desk under the microscope.
Okay.
So take a look at them without magnification. What's that?
A plastic ruler.
And next?
A fingerprint. And then a yellow feather.
Right.
Then I think that's clay. And that one says it's a flea.
That's a flea, okay?
Yeah.
Now, before we look at the rest of them, let's look at the plastic ruler, and so that you kind of understand what's happening.
Okay.
I'll put the plastic ruler here under the microscope. Okay, now the light is coming through from down below, going through the plastic ruler, up here to this long lens, and up here to the television camera. That's what that is right there. Right. Then the image goes down through these wires and ends up here on that monitor. Okay?
TV. Yeah.
So now we can find out how much we're magnifying by counting the number of lines that you see there on the television set. Okay, let me fix it. Get it so it's nice and even, and then you count the number of lines. How many? You,
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11.
Okay. Now, measure the width of the television screen.
Okay. It's about 28
Well, that's
centimeters.
280 millimeters.
Yeah.
Okay. So you divide the 280 millimeters by 11. Okay.
Okay.
And there's the calculator.
280 divided by 11 equals 25.
Okay. So that means when we look at images here at relatively low magnification, we're seeing them 25 times bigger than they really are.
Oh.
Okay. And you notice when you looked at the plastic ruler, see all the scratches and junk on it?
Yeah.
You're seeing all kinds of things.
Yeah.
Okay.
Must be
So
really
now the
scratched
next thing is the fingerprint. You want to hand it to me, please?
Okay.
There is the edge, and here is what a fingerprint looks like, magnified 25 times.
It looks like that stuff is just dirt.
Well, when you take a fingerprint, you actually put some form of dirt, more likely carbon of some kind, and you stick it to the oil that's been left behind when the finger touches something.
Yeah.
So that's why it looks like dirt.
Oh.
And the detectives, when they look at that, would recognize that as a loop. You see how it loops around?
Yeah.
That's one of the ways you identify the kind of fingerprint that it is. Okay, now next.
The feather.
Okay.
I wonder what that's gonna be like.
Now there is what it looks like. Now let me move it down here, or let's go up here to this edge.
Okay.
Or out here to the edge like this. Now, whoops, that's a little too much light. Let me magnify it just a little more by going up and moving it over so that you can see what's happening with the various strands.
You can see the little strands of feather.
Now, you see, first of all, here's one of the sort of veins of the feather coming up, and here's another vein over here. Then there are little things that come off of each of them.
Yeah.
Actually, they hook together.
They do?
And that's what makes the feather nice and strong.
Oh.
In fact, I'll zoom up a little more, and you watch.
Yeah, they do kind of look
See how they are
right there.
Right, they're all hooked together, and that's what gives the feather its tremendous strength.
Yeah.
Okay, what was next?
The clay.
The clay.
There.
Well, I think you'll be surprised. It turns out to be very interesting example of the work of an insect. I'll zoom down to low magnification and take a look at that section right there.
Looks like all kinds of rocks.
Well, they're not rocks. They're actually the loads of mud that a mud dauber wasp collects and brings back to build her nest out of.
Wow.
Each one of those things that look like a rock is one load, okay? Now she builds the whole nest, and I'll turn it over so that you can see the other side. There, you see each one of those lines is a cell.
Yeah.
That's one cell, then the next cell over there.
Yeah. One, two.
Now the reason she does that, she deposits eggs in there, and now give me the other piece of mud,
Okay.
because I'd like you to see inside.
Ew.
Matter, ooh.
It looks like the bugs are still in there.
Well, what happens is the female wasp not only builds her nest like this, but then catches insects and puts them into the chamber so that when the young wasp emerges, hatches from the egg, it has something to eat. And I have an idea that's what's left of some of the insects that she caught and put in there for her young ones to eat.
Yeah.
Okay, what's the last one?
It's a flea.
A flea. Have you ever had an animal that has had fleas?
Yeah.
What do they do when they get a flea bite?
They scratch
They
it.
scratch. And you can see why when you take a look at a flea magnified about 25 times or so. Now, there it is at low magnification. I'll bring it up so we can really get a good look at it and put some more light on it. And first of all, you know how a flea gets around?
Well, does it walk?
They walk, but they don't fly because they don't have any wings. It gets from one animal to the other by hopping. And see those two back legs back there?
Yeah.
They're very powerful, and they can hop maybe 14, 15 times the length of a flea. It jumps like crazy. So it gets around like that. And then when it gets on an animal, then it uses that piercing thing at the front to suck out blood. And that's what makes the animal itch. So that's why they scratch, because the flea is biting them. In order to get some blood, in order for the female flea to use the blood to develop new fleas as part of her food. Anyway, we've used a lot of expensive equipment here to look at things. You just get a good magnifying glass that magnifies 10, 15 times and look at the stuff around you. I think you'll find all kinds of fascinating sights in the microscopic world.
Yeah.
Hi, Mr. Wizard.
Hi, Tarek. I invited you over for a special treat. Pretzels. Have you ever eaten pretzels?
Lots.
Okay. And I have my stopwatch standing by because I want you to tell me how many pretzels you can eat in 1 minute. Very scientific experiment. How many can you eat?
About 15.
Okay, are you ready?
Yes.
I will then start the watch the minute you put the first one in your mouth. Go. 1, 2, 3, 4, 6, 7, 8, 10, 11, 14, 15. How many have you got? One so far? Okay, 19, 20, 22, 23, 26, 27, 30. You're on the second one now? Okay. Oh, 3? Okay, 3. Okay, 35, 36, 37, 30, 40, 42, 44, 45. Stop laughing and eat. 47, 48, 49, 50. You got 10 seconds to go. And you've got 3 so far? Okay, on your fourth. Okay, 4. Okay, 56, 57, 58, 59, 60. Okay. How many did you get? 3? Okay. Okay. How come? I thought you said 15. Do you want to take a drink of water? I got it all set for you. Okay. Okay. Your mouth felt terribly dry, right? Very dry, very dry. Well, as a matter of fact here, while you're finishing the rest of your 4 pretzels, let's take one apart. Because I think if you look very carefully at a pretzel next time, you'll find that inside it's very, very dry. And the reason why one of the reasons at least why it's so dry is that shiny coating on the outside. You notice all pretzels have that shiny coating? Well, in there is a chemical that absorbs water. So whatever water is left after they finish baking the pretzels is now absorbed by the chemical, so inside is extremely dry. And what happened when you started to eat the pretzels, it absorbed the water in your mouth. And as you eat more and more of it, more water is gone. Pretty soon your mouth is so dry you can hardly talk. Well, you couldn't even talk, right? Okay. How about another drink?
Thank you.
Yeah. So ordinarily I don't like the kind of challenge in which you see how much you can eat, you know, because I think that's kind of gross, as you kids say. But in this case, it was a very scientific kind of experiment to show that one of the reasons why pretzels are served at places where they serve drinks is because they absorb water very, very readily from the inside of your mouth. So good. Next time you're challenged, how many pretzels do you say you're going to be able to eat in 1 minute?
3.
3, right. Aaron, there's an old scientific trick in which you plunge a soda straw right through a potato.
Sounds impossible. How do you do that?
Well, here, try it first of all.
Okay.
Hold your hand down here far enough so if you happen to get it through, you don't go through your hand as well, okay?
Yeah.
Okay? Just plunge it. Go ahead,
Will it go
just
through?
plunge it right straight through. See what happens.
I can't get it through.
Now, what you're trying to do, the secret for doing it here, let me even use the same straw, is you have to hit the straw at exactly the right angle, not at this angle or not at the angle, you know.
Otherwise.
Right, otherwise it sort of bends. And I like to pinch the end of the straw like this so I get a good grip on it. Now, have you ever heard the word inertia?
No.
Okay. Well, that means when an object is at rest, it will tend to stay at rest, which is what the potato is, right?
Oh, okay.
Now, also, when an object is moving, it will tend to continue to move till it's stopped by something, and that's what's happening to the straw. So when you put those two combinations together, if you do it just
You know
right,
something through this?
now in that case, I was at an angle, see? So also it's a good idea to have a supply
Flat.
of straws handy because it doesn't always work, but that always adds to the suspense.
What if the potato's not flat? Then it'd be
Well,
harder too.
you have to just sort of keep working until you get it like that.
Yeah.
See, there's a little plug of potato because you went right through and made a little plug. Okay, now you try it.
Okay.
You got the idea now?
I
Pinch
think
it at
so.
the top so you get a good grip. Watch your fingers.
Yeah.
Okay. And
Almost.
Almost.
Halfway through.
okay, halfway. Try it again. A little harder this time. You know what I think?
What?
I think you ought to take the potato and the straws home and practice. Okay?
Thanks.
Can you see my secret message, Larly?
No.
Well, that's because it needs developing. So here's how you do it. Here is a steamer, you know, that they used to fix to get the wrinkles out of clothes.
Yeah.
Just run it over the mirror there and you'll see.
Oh, there's an O and an A. Oh, there's an S and a P.
There you go.
Oh,
See what it
soap.
says?
Soap.
Right.
Why would you write soap?
Well, that's because that's what I used to write the secret message.
Really?
Yeah, well, you know how soap breaks up surface tension of water. Okay. Wherever there's soap on the mirror, the little droplets won't form. They actually coalesce and form into water surface rather than a drop.
Oh,
so
neat.
that's how you can write it. So what you need is some water, add a few drops of soap so it isn't too soapy, and then use a cotton swab and sort of wring it out a little bit so it isn't too wet, so it won't streak,
Right.
and then use that to write the message. So here, write secret message for me.
Okay.
Okay, I won't look. You can also put it on the soapy water onto a cloth, and then when the inside of the automobile gets fogged up, well, you can wipe the inside, and then it won't fog for maybe a whole hour or so.
Really?
Yeah. Okay, you finished?
Yep.
All right, see what the secret message is. Hi, with a circle, okay. Ah, hi, Dad. When does your dad take a shower?
In the morning, usually.
Okay, well then, hopefully, if he steams up the bathroom, when he steps out, you could write this on the medicine chest in the bathroom,
Yeah.
and he'll see the message, hi, Dad. So write the message with soap and develop it with a steamer or the shower.
Can't wait to do that.
Okay, well, good luck.
Thanks.
Here, Sarah, take that steel ball and place it right there and watch what happens.
Sure. Is that sort of a chain reaction?
Well, that's sort of a good guess because that's the sort of thing that happens in a chain reaction. But this is a model of electricity. Now, do you know what electricity is?
Yeah.
What?
Well, it's sort of a charged power.
Charged power?
Well, like charged energy.
Okay. It's energy. That's certainly, it's a form of energy. And when you say charged, I assume you mean that it has electrons and that sort of thing in it. Right,
Yeah.
okay. That's what these balls are. They're electrons. Now think of it this way, that this incline represents a wire.
Okay.
And it's made of a material that will conduct electricity, because that means that there are electrons that are not held very tightly to the nucleus, so they're free to wander around. They're called free electrons. Then when some energy of some kind is given to an electron to push it into the end of the wire, it runs down here and pushes away that electron, because they're all negatively charged and they try to spread out as far as possible.
Yeah.
And that's why they cascade sort of down here, okay, like this.
I see.
Okay. Then notice, by the way, that the electron that you get out of the end of the wire is not the same one you put in.
That's
It's a
true.
different one, okay. Down here, when the electron flows by this part, that represents the energy in the electron that does work. How do we use electrons?
Well, in microwaves.
Right, microwave.
Blenders.
Right. Anything you plug into the
Yeah.
wall, right? TV, toasters, all that stuff. Well, that's what this bell represents, okay? So there are lots of different ways to give electrons a push to get it started. Do you know what some of the forms of energy are to give electrons a push?
Well, hydro plant.
Hydroelectric, in other words,
Yeah.
water, falling water, right?
Yeah, and static electricity.
Well, static electricity, once you rub something, you mean, and it stays put.
Yeah.
In that case, the electrons don't move, because they're usually on a non-conductor, right? And static
Yeah.
like wool and so forth. So that's not quite the same. However, they use heat, right?
Yes.
They burn coal and then generate the steam to make the turbines work. They use nuclear, chemical reaction,
Yeah.
energy from the sun and solar power, right? And in this case, we're using muscular power to give the electrons a push. Have you ever used your muscles to generate electricity?
No.
Okay, here's your chance. This is a very old device to generate electricity. What you're going to do is turn this crank. Inside there is a little coil, and these are magnets. As you turn the coil within the magnets, they're going to push the extra electrons through these connections over here to light the bulb, and then flow back again. So here you are, for the first time, generate electricity with muscle power. Go ahead. Okay, Eliana, there's your problem. This is aluminum powder, very fine pieces of aluminum, stirred up in water. And what I'd like you to do is to get it all to the bottom.
I don't know how I do that.
Well, gravity will, first of all, help you. If you let it sit for a while, it'll all sink to the bottom. What we have to do is somehow get it down faster. You don't know how to do that?
No.
Here's a clue. See this puzzle? There's a little black thing in the middle separating two balls. What I'd like you to do is to get that ball up there and this ball up there.
Okay, I'll try. I can't do it.
Well, that's because once you get this ball up on this side, when you go to get it over on that side, that one rolls down, right?
Yeah.
Okay, here's what you do. Take it by the center there and give it a spin like this.
Okay.
See what get the idea? Now, do you know what force it is that's helping you get the two balls up there?
Centrifugal force?
Centrifugal force. Okay, back up but you don't hit that. Okay, give it a spin. Ha-ha, you did it. Okay, now do you see how you're going to get the metal down? By using this centrifuge. Works on the same idea.
Okay.
Like here. Here are some strange little test tubes with points in the bottom. Pour some of that liquid into here. Okay, now put it in one of these sort of, they look like metal test tubes, right?
Yes.
Okay, pour about the same amount into there. And put it on the other side.
Okay.
Now pour some in this one, and that'll be our control. You know how scientists use controls?
Yes.
Okay. Now, you can see, if you give this handle a twist like that, you see what's going to happen?
Oh, that's going to spin around.
Yes.
And then
Centrifugal force is
will
going to make the
make
metal
the metal
go down to the
go
bottom.
down to the
Okay,
bottom, yeah.
so stand back a little bit and give it a nice spin. The other way. There you go. Faster yet, faster yet.
Looks like it might take off.
Yeah, like a helicopter, right?
Is that enough?
Okay, try it. Well, I don't know. Let's take one out once and see. Okay. Now we'll compare it to the control. Look at the difference.
It went all the way
See
to
it
the
all? It's
bottom.
all the way down at the bottom, right. In fact, scientists have centrifuges that work at extremely high speeds in which they can separate molecules of different weights.
That's really neat.
So it's been a very handy tool. So now for the first time you've used a centrifuge. Give it another spin. Derek, I want you to be very careful because here's a butcher knife, which I have clamped to the stove over here. And I have this little
Yellow dot
pasted there so you can see where the point is. And here's another one fastened over here to the counter. Okay. Now hand me that piece of paper.
This one?
Yeah, here's a loop of newspaper which I'm going to put over here right on that sharp edge. You put the other one over here like that.
Okay.
Okay. Now hand me one of those sticks over there.
This one?
Mm-hmm. Okay, now we're suspending the stick from two pieces of newspaper supported by knife edges. Here is a piece of wood which I'd like you to use as a bat. You know how to use a bat?
Yeah.
I want you to come down here and hit it in the center as hard as you can. Okay, what's going to happen?
The paper's going to break.
You think so, right?
Yeah.
Okay, because it's supported only by that thin knife edge. All right, hard as you can, fast.
Holy. The paper didn't break.
The paper didn't break, and you broke the stick in half.
Holy.
Now, how come?
Because I hit it so fast it didn't have time to.
Well, that sounds sort of logical, but that's not quite it. Speed is important. So let's set it up again. That paper's okay. This one's okay. Now hand me another piece of wood. The reason why the paper doesn't break and the piece of wood does is a thing called inertia. Have you ever heard of inertia?
No.
It's the tendency on the part of an object to stay at rest, if it's at rest, until something moves it. Or if the object is moving, to continue to move until something stops it.
Like a car.
Yeah, it happens in a car.
So if you're going real fast
Right.
and you stop at a red light, the inertia would make you go forward.
Right.
And if you were going slow and stopped at a red light, you wouldn't
You
go
wouldn't
anywhere.
Okay, but now if you were at a red light and you started real fast, there's
Yeah.
a tendency for you to stay still. Okay, well, that's what's happening here. So just to prove it, hit it again, but very slowly.
So
In other
just
words,
like push?
Just push down on it and see what happens.
The paper
Yeah,
broke.
you broke both of them.
And
Okay.
the wood didn't break.
And the wood
this
didn't
time.
break. Okay, now bring two more pieces of paper over here.
This one and this one.
And you know what to do, how to set it all up?
Yeah.
Okay, here, I'll hold that.
Okay.
Go ahead.
Is that good?
Good.
And
There you are.
put the piece of wood in here.
Okay, are you ready? Okay, now why does the stick break and not the piece of paper?
Because of the
Inertia.
Inertia.
Okay, give it a good whack.
Okay.
Very good.